Great, thanks, Aaron. So hope everybody can hear me. I do have 45 minutes, I think. Okay, great, thanks. Let's see if my slides are visible now. Let's see, maybe I'll. Great, so thank you all for coming to this talk and for this wonderful symposium that Starkways has organized. I'm really happy to be here. It's amazing to see all this, breaking edge results from Swastik, from Ale, and from Yael. And I'm not going to be presenting anything new in this talk. In fact, it's going to be a look back at saying, how did we arrive here, and why, a little bit of pedagogy around the results that surround us. So a little bit of a context. I mean, you've seen in Swastik's talk, in Ale's talk, in Yael's talk also, error correcting codes and algebra seem to be playing a very powerful role in designing of interactive proof mechanisms. And the question is, why did algebra have this power? And I hope to convince you by a couple of very simple examples that algebra gives us two very powerful themes. One, resilience. You already heard it mentioned in the context of Reed-Solomon codes. I'm going to reintroduce them, so pretend that you don't know about them already. But I'll tell you about not only the fact that these are giving you amazing error correcting codes, but these are giving you amazing algorithms to accompany these error correcting codes. And so hopefully that's something new. And then I'll tell you why it's so expressive. And this will be an alternate view on some of the things that you're implicitly seeing already. And I'll tell you about the two combining very nicely. The end point of my talk will be the motivation for why we should study Fry. We've already been studying Fry for the last 3 talks. All right, so resilience. What is resilience? So this question of resilience of information, of course, dates back to the 1940s, when we started to think about digital communication as opposed to continuous analog communication. We realized that a natural language like English is not very resistant to minor changes, and complete sentences, changes, meaning of sentences can change completely by tiny changes. So it was important that we design some mechanism to deal with errors. And of course, the search started immediately, and Shannon developed this amazing architecture. Amazing because in 1948, when we did not have computers, he put in 2 computers into every communication system, with an encoder and a decoder, and said, look, if you have these encoders and decoders computing arbitrary functions, what could you do? So these encoders take a small amount of message and expand it to something larger, from k bits to n bits. The decoders squish it back from n bits to k bits. And the hope is that even after you've encoded and flipped some of the bits during transmission, when you squish it back, you get the original thing. Do these things exist? Shannon proved that they existed, and in fact gave you very, very, very precise theorems. I will not tell you about the precise theorems today, but the important thing is he gave these theorems, but these were very non-constructive results. These were results which said, these things exist. I will not tell you about how efficient they are to compute. They may take exponential time to encode and decode. In fact, exponential time to even describe the function. Okay. So these are very non-explicit. So how do you make these things explicit? And this is where things like Reed-Solomon codes first made an appearance. Reed-Solomon codes actually go back to, 1958 or 60? I don't know if anybody remembers, but pretty long back, okay? Even before I was born, leave alone most of you. And here, as we heard before, you can think of the message as the evaluations of some polynomial at some specified places. For simplicity here, I will think of it as the coefficients of some polynomials of some degree d. So if I have a polynomial, for example, I have the message, which is 4 bytes. The bytes are written as numbers from 0 to 255, or 100, 223, 45, and 76. I think of these 4 bytes as conveying a degree 3 polynomial, whose coefficients happen to be exactly the bytes of interest. And in order to encode this information, I will evaluate this polynomial at many places, many more than the minimum number necessary to specify the polynomial, and send those encodings and evaluations to you. And the first 4 values of this polynomial already suffice for you to know what the cubic is. You can interpolate a cubic using 4 evaluations, In fact, it didn't have to be the first 4 places. It could have been any subset of 4 places over here that would have been enough. But the rest is redundancy, and redundancy is exactly the kind of thing that we are seeking in this mechanism. And it is actually optimal redundancy in some senses. So easy facts that we can work out is, one is you don't have to work with integers or reals or rationals. You can work over finite fields. I will pretend that the only finite fields you've heard of are integers modulo primes, but I suspect many of you know many others. Any k values suffice, as I mentioned earlier. You can handle, what this means is if I take this n evaluations and hide all but k of them, you can actually find the degree k minus 1 polynomial which interpolates on these things. So any subset of n minus k values can be erased as long as I tell you where the erasers are and the remaining values are preserved intact, you are in good shape. All of this so far, you can not only think about doing it information theoretically, but efficiently and very, very, very efficiently if you really care about fast algorithms. In this talk, polynomial time algorithms would be considered as good as the best we want, but of course we can have better measures and they apply here. The very impressive thing is, as soon as you say that you can correct n minus k erasures, an immediate property that follows is that you can recover from half as many errors. So somebody can come in and change n minus k over 2 of these values maliciously, knowing exactly what you're going to do to decode, and still not be able to prevent you from recovering the values. Okay, so half of these erasures can actually, half of the number of erasures can be turned into errors, and you can correct from these errors. But the other n minus n plus k over 2 values should be correct. And all of this not only can be done in principle, information theoretically, there is again an efficient algorithm to do it. What I will try to describe to you in this talk is actually how you can correct some of these errors, and that will be one of the first vignettes that we will pass through. But before I get there, a phrase that you've heard today is list decoding. So let me tell you a little bit about what list decoding is and where the origins of this term come from. So why was n minus k over 2 the limit for the number of errors? Well, let's not worry about n minus k over 2. Let's just worry about n over 2. I want to prove to you that n over 2 is the number of errors that you could correct in this thing. Why? I start with some polynomial and give you its evaluations at the first n over 2 points. Start with some other polynomial and give you its evaluations at the remaining n over 2 points. Now, which is the correct message? Obviously, the first half could be the correct, the second half could be the correct one. List decoding says, okay, we are in bad shape here. We cannot uniquely determine what the correct answer is, but there's maybe only 2 answers that will actually describe half of the points. Okay, was there a question there? No, okay. By the way, and feel free to ask questions anytime. If you raise your hands, hopefully I'll see you and I'll be able to hear you too. So there is a possibility that n over 2 errors cannot be corrected, but that's under a very stringent notion of decoding, and for many, many purposes, it's sufficient to say, look, find me a small list of all the polynomials that have large agreement. And as long as the number of polynomials is small and you can find it, that'll be great. Now the question is, can this be done? For how many errors can you actually correct the polynomials? And we believe one of the conjectures going around here, which we haven't completely used because it's not a theorem, is that actually roughly k plus little o of n errors can be, n minus k minus little o of n errors can be handled with list decoding. We don't know if this is possible or not. We believe this may be possible. It's not been ruled out yet. What we can show is, yeah, the number is much larger than n minus k over 2. It's maybe not as large as n minus k. So somewhere between this factor of 2 is where the correct answer lies. So n minus k over 2 is the limit only for unique answers, but you can generalize this notion of decoding to allow the decoder to output a few possible messages, a list of possible messages, and one of these may be the correct answer. Okay. Does the question make sense? Does the notion of list decoding make sense? Questions about it? Yes. Okay. No, just makes sense. Okay. There exists a person for whom it makes sense. Okay. Let me tell you what the list decoding problem is. This is going to say this in math notation. Next slide will say it in less math notation. But what you're given is the parameters of the code, n, k, and t. T, what is t? T is the number of agreements I'm looking for. Okay. How many non-errors? So n minus t errors have happened. So t is the number of non-errors or agreements. And I want to find a polynomial, all polynomials that agree with the list of specified points at t places. What are the points representing? We agreed when designing the Reed-Solomon code that we will send you evaluations. I will send you evaluations of some polynomial p at locations x1, x2, x3, x4, and so on up to xn. So I know x1 to xn, you know x1 to xn. I send you p of x1 to p of xn. What you receive is some y1, y2, y3, and so on to y sub n. What do we know about these yi's? T of these values agree with p of xi. The other n minus t do not. Okay, may not. And you want to find p, or a small list of things which includes p. This is the polynomial problem we want to solve. And the neat thing about this problem is it's actually very, the entire description of the problem is in front of you right now. You don't have to understand the context from which it comes to understand what the problem is. And actually you will see a solution which is pretty easy to describe shortly. And by the way, what we claimed earlier in the previous slides was that if t happens to be greater than n plus k over 2, the number of errors is less than n minus k over 2, then the answer is unique. It can be solved, and it can be found in 1960 by Peterson in an algorithm which was polynomial time. So before the definition of polynomial time algorithms existed, this polynomial time algorithm existed. What we are going to describe to you today is the list decoding version of the question and how to solve it. And this goes back to some work that I did in the 90s with Guruswamy, who was my former student. So, and I'll illustrate this algorithm by picture. So here on the board is, pretend we are working over the reals and pretend we have these little tiny circles are single points. There are 14 of these points in the plane. And what I'm looking for is polynomials of degree 1. Why 1? Because actually our eyes can solve this problem pretty easily. And I hope, can people see the solution over here? Can anybody sort of indicate with their hands? Yeah, so I see a bunch of people sort of drawing these two lines. And yes, there's the x equal to y line, and there's the x equal to minus y line. If you pretend this point here is the origin, there are two lines that solve that fit 5 points. Okay. Any other lines? Anybody who's found any other lines? I hope. Oh, Evgeny wants to find a new line. Evgeny, sorry, you can find lines with 3 points maybe, but not 5 points. Okay. So I want to find things with 5 points. Okay, so I'll claim that the answer is no. And in fact, I'm going to give you a proof that there are no other lines which go through 5 points. And that relates to this algorithm that we're going to find. The algorithm comes from this idea. We're going to find an algebraic explanation of not the 5 points that I care about or the 9 points that are on these union of 2 lines, but all 14 points. Every one of these 14 points has an algebraic expression, which is this polynomial equation, x to the 4 minus y to the 4 minus x squared plus y squared equal to 0. Okay. This assumes that the distance, the radius of the circle is 1, and that origin is the intersection point of the 2 lines. Okay. So that's the polynomial. It's a degree 4 polynomial, which explains every point on the board. And if you just stare at the solution, you can get the 2 lines that you care about, right? Yes.
What sense does the solution explain?
Good. Every one of these points, if you write down its x coordinates and y coordinates, will satisfy this equation x to the 4 minus y to the 4 minus x squared plus y squared equal to 0. Okay, that is a sense in which this curve explains all the points. Okay, all right. So now stare at the solution, because what does staring at a solution mean algorithmically? Means factor this polynomial. Okay, that's what is happening in this picture. So you can factor this polynomial, you will get these things. And there's an x plus y and an x minus y. These are the things that we cared about. These are lines, y equal to x and y equal to minus x. This third thing is just explaining the rest of the garbage out there. Okay? But it's proving to us, look, there's a circle. This circle can intersect any line in at most 2 points. Any other line which passes through 5 points must either intersect this line twice, can't do that, or that line twice, because it must have 2 common zeros with this, or 2 common zeros with this, or 3 common zeros with that. And you can't have those. Okay? So these are all the solutions, and everything on this page is algorithmic. So you can find all low degree polynomials which explain all the points easily. It's just a set of linear equations looking where the unknowns are the coefficients of this polynomial. And factoring is something that you can do easily. And if the factors happen to have factors of the form y minus p of x, so y as a separate term and p of x as a separate term, then those are the things that should alert you, and then you should look at them carefully, those polynomials carefully. So this is the whole algorithm. There's a fact which says that, for example, if I had n points in the plane, there's always a degree 2 times square root of n polynomial in x and y, not degree n in x and y, only 2 times square root of n, which will always be 0 on all of these points. It's a non-zero polynomial. There's always a 0 polynomial. Polynomials can be factored efficiently. This polynomial that exists can be found efficiently, and once you do these 2 steps, you will find all solutions which pass through at least 2 times square root of n plus 1 line, every line which passes through at least that many things. And as you sort of optimize for parameters, you can do better and better and get a lot better. In fact, let me see, how am I doing on time? Let me go through one very quick vignette, which is, we can push this methodology even further. So for example, here is another example here. There are 11 points, and I want to find lines which pass through 4 of these 11 points, slightly different parameters, and then suddenly there are many more lines. Actually, I can find 1, 2, maybe some 3, 4. So there are maybe at least 5 lines that I see over here. So there's many more lines, and if you just try the vanilla method, it actually doesn't work. I mean, if you try to pick the same algorithm that we had from the previous page and said, oh, look, fit it to this data, what's the best curve that you can find? It'll be some degree 5 will be the best you can hope for, and it just won't work very well. Or maybe 4 will work, but it won't be working very well. On the other hand, what you can ask for is find all polynomials which go through each point twice. So have a singularity at each point, and then plot its zeros. And that gives you some solution that might look like this. Okay. And now if you look at it, there are lots of lines here. There are some lines like the blue lines which are not interesting. But then there are all these red lines, and they all happen to be passing through at least 4 points. So this is what is called the method of multiplicities, which has been developed a lot by people like Swastik and Shubhangi since then. And this gives us the state-of-the-art algorithm that we have for Reed-Solomon decoding today. This is from 1998, and there has been no real improvement on this particular algorithm since then. So it's interesting. Anyway, so this algorithm at the end, the bottom line is it corrects n minus square root of k times n errors when you're trying to find degree k polynomials through n points. No constants anywhere that are missing here. Maybe there is a +1 at the end that I might be missing, but yeah, I mean, plus constant should be some things you can actually enumerate over. So polynomial time algorithms, this is accurate. So the summary of this part is that polynomials are very resistant objects. You cannot take a polynomial and change one of its coefficients slightly and get something that looks more or less the same. You make a slight change somewhere, everything changes pretty much. And not only are these information theoretically resilient, they are algorithmically resilient. You have algorithms to match this capacity. So they can correct errors, but now you might ask the question, why should they capture computation? Swastik asserted this by fiat. I will try to give you a little bit more of intuition into why they capture computation. Okay? So what's the expressive power of polynomials and where does it come from? I'll start by a kind of a folklore thing. Everybody should have known this. In fact, if you look at Boole's original paper from, I don't know, 1670s or 1770s or something, I don't remember, it's 200 plus years. It talks about algebra. And so, yeah, I mean, algebra was essential to logic and computation. We've known this for hundreds of years. And you can use that to say that, okay, I can take all algebra and express it using n-variate polynomials. If I have some logical formula involving n Boolean variables, I can express it as, polynomials involving n Boolean variables that need to be satisfied, for which you have to find a common zero or something like that. So it's kind of simple to say if variable, logical variables which have values true or false can be associated with algebraic variables which take values 0 or 1, and then this captures negation and Boolean logic or and pretty naturally, and using all this you can come up with polynomials which capture all the things that we want to do. This is not great for us because these tend to be polynomials involving many variables. We don't like that. So what I'm going to tell you about now is how you can express something very basic to computer science, namely the three coloring problem. Oops, I was hoping for some animation on this slide, but I forgot to put it in, but focus on the first few lines of this slide to start with. So a simple problem like three coloring can be expressed in terms of, basic algebra. What I'm going to do on this slide is not rocket science either. It's going to be just as elementary as what we did in the previous slide, but it captures an interesting problem using constant number of variable polynomials of degree about n. How? So suppose I want to tell you that here's a graph and it's three colorable. And by the way, I mean, three coloring is an example of an NP-complete problem. And the theory of NP-completeness basically says any NP-complete problem captures computation that you care about. If you really care about constants, then you try to worry about which problem am I working with, and you don't always work with three coloring. But in this talk, I'm not going to care about constants. I'm not even going to care about polynomial losses. So three coloring is a pretty good example. I will have a graph. I will have edges between vertices, and I want to know, is there a coloring assignment of vertices, a function a that assigns to vertices a color 0, 1, or 2, such that for every edge, at least one of the two endpoints have different colors. You cannot have 0, 0 as the two endpoints, or 1, 1, or 2, 2. You can express that algebraically fairly easily, but the way I want to do it is by viewing the vertices as elements of some fields. ZP is good for me today. It's a subset. The vertices are the elements 1 through n, which is a subset of a large field. I want to tell you what are the edges. The way I'll tell you what the edges are by giving you the edge function, which is a function from v cross v to 0, 1, right? I mean, I just have to tell you, given the name of the two endpoints, is there an edge between them or is there not? That's how a graph can be described, and you can, if you know the graph, you can build this function yourselves. And then the other thing that you can do is to extend this to polynomial over entire ZP, whose evaluations will not always be 0, 1. There'll be values in ZP, but the degree of this polynomial will not be p, it will be n. So whatever p you take, the degree of this polynomial will be at most 2n. It's a polynomial in two variables, okay? That expresses the input to graph coloring. I give you this polynomial, and then I just specify the subset of variables that corresponds to the vertices of the subset of the field that corresponds to the vertices, and I say, is there a function a of this type that's available? Is there, oops, that should have been a. Is there a function a which has the feature that a of x is always in 0, 1, or 2 as long as x is between 1 and n? Should be a three color ring of the vertices, not an arbitrary coloring. And for every edge, either the edge is not present, in which case I don't care, or a of x minus a of y should not be 0. And if it's not 0 and the coloring is 0, 0, 1 or 2, the value of the a of x minus a of y will be either +1 or -1 or +2 or -2. So this very simple degree 5 equation in E and A express the constraint that a graph is 3-colorable. Okay? So this is a very simple description of how we go from some arbitrary combinatorial problem to something very algebraic. Is there a polynomial A, sorry, that should have been A, whose degree is at most n, which has these constraints everywhere for x between 1 and n, and these constraints everywhere for x and y between 1 and n. Does this make sense? 3-coloring expressed algebraically, not rocket science. The interesting thing about this is it allows us to start thinking about how you could prove 3-coloring. And the claim is that I can actually, based on just this previous reduction, this page, and I'll tell you the key on the next slide, I can create a proof for 3-colorability, which will ask you to write down the values of 4 polynomials. Some of these will be in 1 variable, some of these will be in 2 variables. 4 polynomials, A, B, C, and D. You will just write down a value of all the evaluations of this polynomials, and as long as the inputs are in ZP. The values are, there are 2 variables that take values in ZP, so the size of this thing is order of p square at this stage. And p will be somewhat larger than n, so that will explain how large this is. In order to verify the proof, all you have to verify is that some operator, a local operator on A, B, C, and D, and I'll describe the operator on the next slide. This operator will produce a polynomial in 3 variables. This polynomial we will prove will be if this polynomial turns out to be the identically 0 polynomial, then we know that the original graph was 3-colorable. This proof requires you to be able to work with the function E. You should know the function E, for which the edges of the graph, you should know it. Otherwise, of course, I can prove there exist graphs that are 3-colorable. You should know the function E. You should be able to evaluate it wherever you want, but that's all you need to do. Where is this local operator coming from? It's just coming from what we did earlier, expressing 3-colorability using 2 constraints, and those 2 constraints somehow work into this operator. This operator, let me just explain to you what it's doing. Phi of A, B, C, and D will be a polynomial in 3 variables called W, X, and Y. If you want to evaluate it at any one value of W, X, and Y, you just go through this formula and plug in the values. And you notice that this thing has some constant number of values of A at X, A at Y, B at X, C at XY, and D at XY involved in it. Okay, these are it. Constant number of values of the polynomials that you're interested in is all we are looking at. Why is this polynomial supposed to be identically 0? Well, if you notice, there's this variable called W that appears only once. The only way this whole polynomial will be 0 is if the coefficient of W is 0 and the constant term is 0. The constant term is basically just verifying, and this is the one thing that I'm actually glossing over, but it's a methodology from a work that I did at Elie Ben Sasson in 2004. So it's a neat fact. The only way this polynomial A of x times A of x minus 1 times A of x minus 2 minus B of x times this polynomial, only way this can be 0 is if A of x is taking values in 0, 1, or 2 on all of x between 1 to n, okay, on all of this domain, V in V. The second term similarly verifies the validity of the coloring for each edge. Make sure that each edge is validly colored or is not an edge in the graph. This is a 3-coloring of the vertices, but it may not be, oh, what is the, this polynomial is some degree 3n polynomial, which has to be 0 and n places, where x is for all values of a of v, for v in capital V, it should be 0. This condition verifies that holds. Right. So it takes a little bit of work. I mean, this is not everything on the slide is immediate, but the claim is the full proof is the full construction at least is in front of you. All you have to do to build a verifier for 3 coloring is to put this all together. You say, look, this is the identity I want to verify. So ask the prover to provide tables for A, B, C, and D, and then verify that this for a random value of W, X, and Y, this identity holds. Well, this is almost it, but not quite. What I've hidden here is, of course, this is great if we know that A and B and C and D are low degree polynomials. But the prover is free to write whatever table of values they want to write. And this is what motivates the low degree testing problem. You can take, if you had a solution to the low degree testing problem, you have PCP in front of you, probabilistically checkable proof, but you need to be able to test this. And a lot of work goes into this. So I will not get into the subtleties of how to design a low degree test. I'll say a few words briefly about it, but I want to instead go take a digression into perspective and philosophy at this stage. And I feel, as a person working on information theory and coding theory, I think error correcting codes and polynomials in particular are the glue that allows data to exist. Okay, I mean, if I look at data out there, it's just a zillion collection of bits, and there is no, coherence to it. There is no structure to it. You can take a sack full of the sand, throw it out. Nobody might note the difference. You might replace it with some cement, no problem. It's very, very hard to look into this thing and find any structure. What does polynomials do to these things? They build some structure using these objects. They just assemble them together in a glue form. You build a wall using all of this, maybe not sand, but take the right materials that work for building walls. They glue these objects together. And that's really what happened. You had all of these bits, and each one of these could have had any value in 0 and 1. You took a polynomial, built on them, and evaluated at a few more places, and suddenly you get this completely rigid object that you cannot move at individual places. You have to take the whole thing and change everything about it completely in order to get a new polynomial or anything that even looks like a polynomial. And why are these walls useful? Not just because we want to build walls, but because you can build entire structures using a few walls. I mean, if you look at this room that we are standing in, I see about 6 walls, maybe 7. So a few rigid objects completely define any one of these structures that we care about. And what's happening is PCPs is very analogous. A constant number of polynomials can capture things that we want to say about n different bits. The fact that these n variable values can all be assigned so that the graph is 3 colorable, all vertices can be assigned, can be expressed with a constant number of polynomials, not with n polynomials. So there's this amazing quantitative leap. And if you think about how you inspect buildings, this is how you go around. I mean, you don't go around saying, let's look at each atom that was used to build this building, and let's explore it and find out whether it's sort of, bonding correctly with its neighboring atoms. We sort of reduce the verification paradigm to saying, let's make sure that each wall is actually a structurally sound wall. And so somehow maybe you tap on the wall, you knock on it, you do something. That's the low degree test. We are going to go looking at these pieces of polynomials and look at them and say somehow, oh, are these really polynomials? Is this rigidly defined? And then we just say, oh, are these polynomials sort of, built in the right way? Are the joints correct? Is the structure correct? Did I put the right supporting material in the right places? And then the building is deemed integral. PCPs are working exactly the same way. In order to design the integrity of useful data, we first test the integrity of the walls, which is the low degree test, and then test for structural integrity, which is this testing of this condition. Okay, and that's it. This is an entire PCP. So I feel that this is sort of very neat, but of course it motivates this question called the low degree testing problem. And I've summarized it over here. We, again, so the top part defines the problem. I'm given some arbitrary table of functions mapping ZP to the M. I'm thinking of an M-variate function. In the examples today, we thought about M equal to 1 or 2, maybe 3. Actually, we never needed to test a trivariate function. We just wanted to test that the final trivariate function was identically 0, which is kind of simple to test. You just pick random points and see if it's 0. What we want to do is query the function in a few places and then check to see if it's a degree D polynomial or not. So if the polynomial has degree D, then we should accept it. If it's far from degree D polynomials, if it cannot be decoded into a degree D polynomial uniquely, then we want to reject it. This is the task that was underlying Fry and Stir and Deep Fry and lots of other protocols. They did it in a in an interactive IOPP setting, but you can define it in a non-interactive setting. There are lots of theorems. This slide, I should warn you, is missing lots and lots and lots of references. And the reason, I had time to put together all the rest of the talk, but I didn't have time to write down all the references that could go here. So I'm omitting references here, but trust me, this theorem here that I'm stating in the middle of this page is not a simple theorem. It's a huge body of work which says, yes, you can do this. But even what you can do with this is not great. At the end, it says, oh, I can test whether something is a degree D polynomial using D queries. Apply it to Alice's problem from earlier or from Swastik's problem from earlier, you're going to say, oh, I can test a degree N polynomial using N queries. I mean, who cares? That's not very useful, but it does provide the machinery that we want. The important thing in these theorems is that it doesn't depend on the number of variables. The query complexity does not depend on the number of variables at all. And you can use this powerfully. If you go back to some of these slides that I was using, let me see if I can, yeah, let's say, I was actually using bold letters for X and Y. Why was I using bold letters? Well, it's a subliminal message. You can think of it as saying, you can treat X as a univariate variable, if you will. This whole thing makes sense. You can also take X to be a multivariate variable, and the whole thing will still make sense. And now you are left with testing a multivariate polynomial. Why is multivariate interesting? Well, because you can sort of squish the degree a lot by going to larger and larger and larger number of variables. So you can just apply the whole machinery and use a slightly larger number of variables and get all kinds of interesting results. So in particular, if you go to M-variate polynomials, the degree can be squished to D to the 1 over M, and by playing with values of D and M, you can get all kinds of very interesting results over here. So that's one thing, but then you can use other helpful information, extra information from the prover. Sometimes you can even do this without interaction. You just ask the prover to provide some extra information about the function at hand and go away, and then the verifier comes in. Or you can have the verifier walk in and say, oh, look, I look at the table, I've seen these values, now give me a new polynomial, etc. You can, design interactive Oracle methods also. All of these mechanisms help us test for low degreenness, and there are remarkable results out there, and I'm not the best at knowing all of these things, but the query complexity does reduce quite a lot. In particular, there are ways, and in fact, even in the paper with Ellie, we gave methods which would, use query complexity, which is sort of maybe in one of the papers with Ellie, we had results with query complexity order of 1 for solving this problem. All right, so to summarize, algebra is giving us very powerful tools. It's not just to preserve information, but to also verify properties of information. The fact that it's good for expressing information, Rees-Solomon codes existed from 1958. The fact that they could be corrected algorithmically, I think, was known in the 1960s, and then forgotten in the 70s and 80s and had to be rediscovered in the 90s, and now we really are on top of it. And the other nice thing about it is that the tools are basic, and that's why we are able to do so many things with them, with like stir and fry and deep fry and circle fry. So the tools are very adaptable, and if you want to change something, you can do it and try to ask the question, can I now analyze it for a change? And it's very feasible. And finally, also something that's sort of that is becoming noticeable nowadays. I mean, I do remember the first time I wrote a paper on Reed-Solomon codes, it took me about 2 years to realize that I was not hiding any numbers behind hidden constants. And that actually these constants can be interesting. And you know that if you have a code of rate 1/2, then its relative distance is also 1/2. It corrects a quarter errors, fraction of errors, you know, in polynomial time. So these are very, very good you're not hiding behind large constant factors in these results at all. So that's another virtue of this algebra. So that's where I find the power comes from. Okay, thank you. Question, oh yeah.
Thanks for the talk. So kind of a historical question. How different is the so-called Berlekamp-Welch algorithm from the Peterson result that you cited, and whom should credit go to?
Okay, great. That's a great question. So in fact, it's a perfectly timed question. I should probably pay you after the talk for for asking me that. The question was, there's an algorithm due to Peterson from 1959, which, by the way, sort of was also forgotten, and then came along Berlekamp and Berlekamp-Massey, and then Berlekamp-Welch. In my opinion, I mean, even in Berlekamp-Welch, if you read the patent, and I have the patent available, the text of the patent available for you, it says, look, we want to solve the Reed-Solomon decoding problem. After a couple of pages of reduction, we will reduce it to the problem that we had on the slide here. And we will solve this problem, and then we will go back and recover the Reed-Solomon code. So they were working with a very different definition of Reed-Solomon codes, which is equivalent even in Welch-Berlekamp. But Welch-Berlekamp had this nugget of an ingredient saying, look, you just have to find a polynomial which fits data in many places. The result from Peterson is vastly different from the Welch-Berlekamp in the following aspect. Peterson's algorithm actually relies on an algorithm to find sparse polynomials through its evaluations. So if I have a polynomial which has only t non-zero coefficients, and I give you its values at 2t places, 2t very carefully chosen places, then I can find the values of these coefficients, even though the degree may be pretty large. It relies on that. And this entire sparse polynomial methodology went out the window in the Berlekamp-Welch method.
Any other questions? Okay, so thank you very much, Madhu.
Thank you.